Hello, everybody. Welcome. Thanks for taking the time out of your day to come hear me talk. My name is Rick Houlihan. I am the Director of Developer Relations for Strategic Accounts at MongoDB. This is my 8th reInvent. I've been a long time, obviously, at AWS. I was the worldwide leader for NoSQL services at AWS this time last year when I was speaking on a stage very similar to this. My passion is NoSQL technology, as some of you may know. And I believe the technology is about the future. And so in this session, I'm going to talk a little bit more about why we need to make that decision. A lot of times, in the past, I've talked a lot about data modeling. We're still going to talk a little bit about that. But what I find in the engagements I have these days, it's more about understanding why would I make a decision to use this technology. And actually, this is something that we went through at Amazon, and we'll talk a little bit about that. Why did Amazon choose NoSQL? Right? Why does a company like an enterprise, a global enterprise like Amazon, choose to throw out a foundation technology like the relational database and go to a NoSQL-first mentality? And it's not because we liked it. Okay? It's because there were really good reasons for that. And so we'll talk a little bit about that and what was it that we went through, right, when we went through this decision? What was the process we went through to make that decision? What was the path that we followed, to find database freedom, right? And really that's what it was when it comes down to it. The relational databases are the chains that bind us, and we'll get into why that is. And to do that, we need to understand a little bit about modeling the data and what is the difference between modeling relationships in NoSQL versus the relational database, because that's where the rubber hits the road, right? When we start talking about efficiency and time complexity and cost of infrastructure, it really becomes apparent. It's like a mathematical equation. So we're actually going to break down that math a little bit, and we'll talk about what it takes to model relationships in a NoSQL database. And a lot of people these days are talking about how do I do it? Right? So you may say it makes sense. This is why I might do it, but how do I do it? How do I take an organization that might have thousands, tens of thousands potentially of developers globally distributed, and how do I make that organization move forward and march to the beat of a new drum? And this was a process that we built at Amazon as I went through the Amazon retail organization. And some of you may be familiar with the deprecation of 3,000 Oracle Server instances and migration of thousands of application services, and that project we called Rolling Stone. Right, so we'll talk about how did we do it and how did we manage that technology transformation at global scale. And then I'm going to break down the thinking. Right? I always like to talk to developers about what is the difference between modeling an application in a NoSQL database versus a relational database, and what are the concerns they need to have going into that exercise? What are the differences fundamentally? Because this is really what it comes down to is developers, they're extremely smart people. Right? You're all very smart people, and you can follow trails very well, but sometimes finding the path, right, can be a little bit difficult, and that's where my team comes in, and we help developers find that trailhead, so to speak. How do I get started on this project so that you can start to realize the benefits of this new technology, right? So first thing we need to talk about a little bit is Amazon. Right? What was Amazon? What is Amazon? And why did they make that decision, right? And things that people kind of I guess they say a flawed assumption, or it's just a general assumption, is that Amazon was a business that was born in the cloud. And it wasn't, right? Amazon was born in 1995. The cloud did not exist in 1995. The first EC2 instance was launched in 2005 or 2006, right? So none of those services were enterprise ready when they showed up. So the Amazon retail organization actually operated on its own without AWS for many, many years until 2014 and 2015 when they started kind of playing around with some of these AWS services. But the reality was it was a traditional IT organization. As a matter of fact, it was a $5 billion company when SOA, when service-oriented architecture became a standard. So that's a large enterprise at that point. We were already grown. We had lots of monolithic applications and services under the hood when you started looking at the actual Amazon retail operation. So it wasn't something that we could just say, hey, it's just a bunch of little services. We're going to chop these things up and load them into RDS instances and be done with it. Right? There was a big process we had to go through to get some of these core monolithic applications that ran the business and transfer those to a NoSQL backend. Just to give you some of the ideas of some of the scale that we were looking at. By 2018, we had 3,000 Oracle Server instances, I mentioned. We were the largest Oracle license in the world. We had the largest Oracle rack deployments in the world. And it was a real sore point for the business, especially for AWS, when Larry Ellison's going on stage and saying, if your databases are so good, then why is Amazon Retail my largest customer, right? So obviously, Jeff Bezos said, I'm not going to let that happen much longer. And he gave Werner a mission. And he said, look, get us off of this Oracle thing. All right, and that was the first mission. That was the first goal of Rolling Stone. It was not replace the relational database, right? It was replace Oracle. Okay, that was the real mission. And a bunch of things happened along the way that we'll get into, but at the time that this happened, we had 10,000 application services, we had 25 to 30,000 developers distributed globally around the organization, and it was a massive undertaking just to think about moving this stuff from Oracle into alternative relational technologies, right? The cost of the relational database was an enormous line item. That was what was driving this. Again, the biggest Oracle license in the world, the largest Oracle rack deployments in the world, and it was just, the check was too big, okay? It was the high infrastructure cost of that, and the high TCO cost of that infrastructure was just too much. There had to be a better way to make this work, and so that was really the decision that we had to make, right? Again, the missions get off Oracle, find a better way to do things, and at the time, the idea was we're going to break things up. We're going to go and tackle the monoliths. We're going to break up these microservices and move them into silos, deployments of RDS, right? That was the idea. Okay, but something happened along the way when Werner started actually investigating things, and it comes down to the same thing that happened many times in history. If we look at the history of data processing, it's about a series of peaks and valleys and what I call data pressure. Right? Data pressure is the ability of the system to process the amount of data that we're asking it to process at a reasonable cost or a reasonable time. Right? When one of those dimensions is broken, we have a technology trigger in our industry, and we've invented many things over the years. Right? The relational database was not here 1,000 years ago. We had many things. We were born with a great database, right? The one between our ears, highly available, right? Questionable durability, zero fault tolerance, single user system, right? We're not going to build enterprise services on this. So we started doing something to store structured data, which is the definition of a database. We created a system of ledger accounting, and we started writing things down. And this really drove public and private sector service for many millennia until the 1880 US Census, right? And Herman Hollerith comes along, and he has to process all that data, and it takes him 8 years of that 10-year cycle, and he knows it's broken. We got to invent something new, and he invented the machine-readable punch card, the punch card sorting machine. Rapidly, we started to push the edges of that technology and find new boundaries as we started to explore what this new technology can do. Paper tape, magnetic tape, distributed block storage, random access file systems, hierarchical management systems, the precursor to the relational database. And in 1980, around 1980, a man named Edgar Codd delivered a wonderful system that we've been writing for the last 40 or 50 years. It's called the relational database. But you got to understand that Edgar Codd himself did not believe it would ever be real. And why? Because he actually bought into the criticism of the fact that the relational data model is a high complexity model. It would never be suitable for transactional applications. It would be very good for OLAP applications, for analytical use cases where maybe ad hoc queries need to be supported. That was his mission. He wanted to create a system that allowed people to ask questions of their data without writing code. Because in the day that he was working, if you wanted to write a query, it was break out the compiler and whatever Emacs and start writing C, C++, if you're lucky, maybe Fortran COBOL or something, but there was no structured query language, right? So you had to write code. That was his mission. But the reality was that the transactional processing systems at the time built on the hierarchical management systems of the day were more efficient than the relational database. But this little thing called Moore's Law came along and it balanced the checkbook. It made the pain go away. It didn't eliminate the problem, but it made it less noticeable, okay? And this was the way things worked, for many, many years until about 2014 when all of it broke, okay? And this is no joke. These are the top 500 supercomputing clusters around the world. This isn't talking about database technology, but it's talking about processing power, okay? The supercomputing clusters, they're trying to get every petaflop they can, right? They're deploying every innovation they can to speed things up as much as they can. And since 2014, they have not been able to meet Moore's Law performance predictions at all, very rarely. Why is that? Okay, the reason why is because Moore's Law is not a law, it's a financial equation. Okay, the more how much is the industry willing to spend to double the transistor density in the CPU every 2 years? Not enough in the server processing space, right? Where we see that 5 nanometer CPU is right here, this mobile device, because this is a lost leader. Okay, I can sell this to somebody, I'm signing them up for 5 years of subscription services. That doesn't work with the server CPU. Okay, so there's no ROI for a server processing manufacturer to go down to 5 nanometer fab. It's too expensive. Moore's law is broken. It isn't getting fixed, right? Per core performance, power consumption per core across the board, it's not getting any better, and the relational database is not getting any more efficient. And this is exactly what Werner's team saw. When we started actually breaking down the problem and looking, what is the cost problem here, right? The storage, on the other hand, storage cost continues to fall, right? So obviously, if the trade-off here is time complexity versus cost of storage, I'm going to win with going with a database that doesn't require those complex joins. And we'll break this down in a second when we get into the actual model, but this is not new thinking, and this is not me just telling you this. This is the words of the man himself in the paper, his seminal paper on normalization, right? It's an advantage for storage purposes because of the deduplication of data on disk. It's an advantage for bulk transmission of data. However, for denormalization will accelerate and increase the efficiency of your CPU for some of your access patterns. Now think about this. If you think about OLTP applications, what do? They run at very high velocity, right? We want these things, transactional applications. They run very high frequency, and they run the same queries all the time. So if I can increase the efficiency of the CPU for my common queries, I'm going to dramatically improve the cost profile of the infrastructure I'm running on. And this is the key learning when we broke things down, and we'll see this in a second. The other thing that Edgar Codd talks about that we do commonly today, I see this all the time, we over-normalize everything, right? We'll have like, some sort of event type table that might have 10 rows in it, or whatever, 5 rows, info, critical, warning with some labels, and we'll join that in on every query. Every time you join a table in an SQL database, you're burning CPU cycles. When you're burning CPU cycles, you're paying for infrastructure you don't need. Okay, so when we break things down, and you start thinking about this, we'll talk about the model in a second, but when it comes down to it, and you think, when NoSQL, right? When and why? There used to be a line between the two, and you'd say an OLAP workload that requires those ad hoc queries, that's better suited for a relational database. But today, NoSQL databases are not really NoSQL. They're no RDBMS, right? Because all of us have, not all of us, but a lot of us have SQL read APIs that'll handle those analytics queries, right? They may not run as efficiently or as quickly as a relational database, but guess what? OLAP workloads do not run at high velocity. I don't see 1,000 OLAP queries a second, okay? They're random, they're ad hoc. The user that's running them is typically executing some sort of troubleshooting, maybe some analytics that they're running, for some use case they need to get a report on. Do they care if the query comes back in 100 milliseconds or 10 milliseconds? No, okay? But when I'm running a transactions at thousands of times a second, then I do care. And that's when we get into actually tweaking the data models, right? So when we talk about making it all work and making this, so we talked about, this NoSQL database, it doesn't join data. So how does it satisfy my workloads? How do I run queries? How do I get my access patterns that are meaningful? Because it's all about relationships. The data, every bit of data that we store is relational. There's no such thing as non-relational data. I don't know what it is. If anyone in this room can explain to me what non-relational data is, please do, because I've been in this business now for, 20 years. I've been working in database technology, NoSQL for the last 15, and I've never figured out what it is. It's the data on the hard drive before you format it. Okay, that's non-relational data, right? It's the static in the air between the radio channels. It's the stuff I don't care about, okay? It's the noise between the stars. What I want is data that I care about. The records are associated to a customer, the history of an order, right? The things that are important to me, it's all relational. If I can't express those relationships efficiently, I can't use the database. That's the key, right? Access patterns are what drives cost in the relational database, okay? When Werner went into the exercise of figuring out what are we going to move and how are we going to move it and where are we going to move it to, a very interesting thing came up. Okay, 70% of the access patterns across all 10,000 or so of those services were for a single row of data on a single table. Another 20% were for a range of rows on that single table or on a single table. And if you think about it, it makes perfect sense because OLTP access patterns are very write-heavy. They're not read-heavy, right? We might have some reads in the mix, and we do, of course, but writes are always affecting a row or a range of rows or an updates, right? They're inserts, updates. They're not going to affect, multiple tables, across multiple tables for the most part. But what was interesting was when we went into the exercise of actually starting to map these workloads into a NoSQL database, what became apparent was with the relational data model in a NoSQL database, it became very apparent that 50% of the infrastructure was there just to support the other 10% of those access patterns. Because when you start joining tables in the application layer, boy, you see how much stuff really costs, right? I mean, the relational database, that hides it all from you. It all happens behind the, the query API, but it's still doing all that work, right? When I'm storing data in multiple places, this is not a good thing. And when we break down the data model, it becomes apparent immediately that something's wrong here, okay? Let's look at a normalized relational model for a simple product catalog. Think, Amazon simplified, right? I've got products, we've got books, albums, and videos. I've got one-to-one between those tables. I've got one-to-many between albums and tracks. I've got a many-to-many between videos and actors, right? All the common relationships we might think. And if you think about all the queries I might have to run, right? Multiple different queries, multiple types of queries to get a list of products, right? Different levels of complexity, and we'll break this down in a second. Eventually what's going to end up happening here, if you think about the access patterns, they're all product-centric. Get me the information for this product. Get me a product by ID. Get me the product by category. Get me products by price that have these attributes, whatever. Everything's product-centric. So the reality is you'll probably end up putting a cache in front of this database to cache the product query, so you don't have to compute the result off of these tables every single time. But what's that do for you? That just adds another layer of complexity, right? And then I have to worry about cache validation and all that kind of stuff, or invalidation, whatnot. The reality is, if the CPU's hopping all over these tables to assemble the view I need, it's not going to be very efficient. Maybe I would choose a different pattern here. For this particular service, where I have a product-centric access patterns, again, get product by ID, get product by type, whatnot, maybe collapsing all those rows into an embedded document structure like this, right? A single object is a better approach, because again, 99.99% of my access patterns are going to be reads by product ID or type or whatnot. I want the join data. Okay, every now and then product information updates, so what? My write's going to be a little expensive, but that's the infrequent pattern. We always want to optimize for the high frequency pattern, not the low frequency pattern. So in this particular case, we want the pre-join data. This actually works really well. In other use cases, maybe not. Right? This could be a real problem if maybe the individual data, individual rows updated frequently. Right? If you think like order history. Orders have items, they have shipments and invoices and payments and whatnot, and all that stuff might get updated independently of each other. Well, maybe I don't want to read the whole document every time I need to update a single item within it. This was one of the big problems we found at Amazon, was you can't oversimplify the data model like this in all cases. In some cases, it works really well. In this particular product catalog case, this is a really good way to model the data. In others, not so much. But let's break down the time complexity here, and it becomes immediately apparent what's going on and why the relational database is dead. Okay, because this is what it does. Let's put some data on there. Look at these joins. Time complexity down below. One-to-one join, not too bad. Okay, one-to-many joins, starts to get a little worse. We get down to the many-to-many. And for those of you who are real DBAs, you'll look at this SQL and say, I haven't seen anything that simple since, I don't know, I was just learning about this stuff, right? I mean, in prod, these queries are going to be a page long, and they're going to have nested SQL inside. And so think what those time complexity of those queries looks like. It's tremendous. We never notice it because the CPUs have gotten so efficient over the years, it hasn't been a big deal. And CPU efficiency is just continually increased over and over and over again. So it's like it's always been kind of a pain or a little sore, but it's like that little sore back you don't worry about too much until you get to be my age. Then it starts to hurt. The reality is, these days, we don't want to do this kind of stuff. If we look at model joins, and I can show you a couple things here that are really interesting, aspects of the document model, aspects of NoSQL. But the first thing we're going to do is take a basic document structure that describes one of these objects, a product, right? This product is going to have some attributes that describe the product inside of that data blob, right? That data object, that's the stuff that describes the product, but I really don't care about from a querying perspective, right? Things like, in this case, the price, the ISBN, whatever. It could be a whole bunch of data in there. That's the data I'm trying to get, not the data I'm querying on. Objects always need to be related to each other, right? In many cases, it's not about just getting an object. In this case, maybe we have many other access patterns besides get product by ID. Maybe I want to get all the books written by an author. Or I want to get all the songs that were performed by a musician, or so on and so forth, all the movies an actor was in, right? So there's always other access patterns besides just get this, right? Key value access patterns are interesting, but not always the useful. So in a document database like MongoDB that supports multi-key indexing, which is really critical here, we can express relationships between the documents as an array of pointers within the document itself. So here I've got an array of a target array that tells me what all this thing is related to. In this case, I'm related to the author. The book is related to itself. It's related to its publisher. It could be related to many, many things, right? Essentially what I'm doing is I'm creating an adjacency list. I'm drawing, or a graph. And if you think of this target array, these are like the rows from your mapping table, your relational model, right, to describe that many-to-many, or they would be the edges in the graph database, right? What I'm trying to do is inform the system of what's related to what, right? And so we're going to build all these objects. The nice thing about these access patterns now is, again, time complexity here. As I go through these base documents, they might contain the information that I'm most interested in about this book, so I can select by the book ID, time complexity, O log n, select by the album, right? I can see all the songs that are on the album and whatnot, maybe not the details of those songs because I really don't care when I'm just looking at the album. I just want the song list. Again, O log n, it's an index lookup. I'm just getting items here. These are key value access patterns. But again, this album's related to many things, related to all the songs that are in the album, the musicians that performed it, the producer that produced it, so on and so forth. And again, all these access patterns are O log n, okay, on these objects. Even the movie object where I have that many and many join. But it gets more interesting when we start adding additional objects. Okay, so now I'm going to throw in the directors, the actors, the song documents, all the things that describe everything that these things are related to. Again, these things also have target arrays telling me what they're related to. Every document's related to itself and a bunch of other things. Now, when you index the target array in a multi-key index, I'm going to get to see it's essentially it's a lookup index on that target array. If you think about what the relational database does, at its core, when things are configured properly for high velocity reads, it's going to take two indexes, one on table A and one on table B, and it's going to merge them, right, on a shared attribute. If I put all these documents in a single container and I index them on a shared attribute, they're already joined. I don't need to merge the indexes anymore. So now, when I want to get all the books by an author, I can select by target ID as Mary Shelley. I get every book that she wrote. I'll get every person she's related to. Anything in this adjacency list that has a relationship to this person will show up by selecting where the target ID is the author. Similarly, selecting by song ID brings back all the albums that the song appeared on, all the musicians that performed it, the studio that recorded it. Whatever I need to retrieve, I can have any number of access patterns now on a large number of dimensions. And the neatest thing about this, I haven't denormalized any of the real data. I denormalized the pointers, right? There's no mapping tables anymore. We're used to seeing those between a many-to-many relationship. Yeah, the mapping table kind of gets denormalized across the objects here, but the multi-key index keeps track of all of that data duplication that would be required if I didn't have that feature. Right? So that's one of the key features of the document database is the ability to express relationships extremely efficiently using these data structures. Right? So you get down the list here, select where the target ID is Tom Hanks. I'll get every role, every movie he was in. He might be a producer. He could be, a publisher or whatnot, and again, I can select every piece of work on multiple criteria. I just create a compound index to support that. And the best part about this is that many-to-many join, right? That one all the way down there at the bottom that we were looking at earlier where the time complexity starts to explode. This is the same join here. In this particular query, just selecting where target ID is movie title, I'm going to get every actor that was in it, all the data associated with those actors, basically all those documents returned in that query. It's one round trip to the database. The time complexity is O log n. And what does that translate to? A massive amount of infrastructure reduction. If you can reduce your query complexity, time complexity, and this is what it is, right? Developers will spend hours and hours and hours optimizing their code to make it, to reduce that time complexity in the code, and then you hand it off to the ORM and say bye-bye, and you see what happens, right? And that's the foundation of the application. If you're not optimizing the data model, and I always said this with the relational database too, if you're not worried about your access patterns and you're not optimizing the data model, then essentially you're building a wobbly tower of technology, right? You're not building an application. Because if you're handing off to an ORM, it's going to do really ugly things, okay? So the best idea here is to pay attention to what your access patterns are, create these pre-joined data structures, leverage multi-key indexing, and reduce the time complexity of your high-velocity queries. And that was the key learning. If you think about it, 90% of the access patterns at Amazon, again, for a single table, a single row, or a range of rows on that table. So they're very simple. They're working with small bits and pieces of data, but the 10% that join everything, right? Those are the ones where the infrastructure cost is felt. So if I can reduce the time complexity of those joins and maintain the cost efficiency of updating small items, then I'm going to have a win-win all the way around. And this is why, actually one of the reasons why the document database is really a vastly superior solution. I can simulate this in other databases, but it requires me to process a change stream and maintain in code all these updates across all these partitions on the table or whatnot. We do this for you in MongoDB. Okay, so nice to talk about this stuff, but the reality is when the rubber hits the road and you got developers that need to know how to do it, I always say there's two sides to developer relations. Okay, there's advocacy and there's enablement. Advocacy is what I'm doing right now. I'm up here, I'm talking to you, and you're looking at it, taking pictures. Oh, this is great. Now, when you walk out of here, what did you learn? I don't know. You maybe learned some things, but you didn't learn how to solve your problems. Right? You all have problems you're working on. You have applications and services. They have data models. They have access patterns. I didn't talk about any of those access patterns. How do I model all that stuff? So that's the enablement side, right? And that's what my team does. One of the things that we found at Amazon was that if you want to have success in a technology transformation, it's about getting to that early majority. If you look at the bottom of this chart here, this is the technology adoption curve. And when you get to the early majority, it's telling you that the ecosystem that you're looking at, they know what they're doing. Okay, before then, they really don't know what they're doing. There's a technology trigger in our space. This is data pressure. Everybody hears about it. They have the same problem, right? Oh, my relational database is too expensive. NoSQL is going to solve that problem. Let's all go use it. And what happens? You have a miserable experience with it because you start to try and use it the same way that you use the old technology. That's how it's familiar. In NoSQL today, biggest problem out there, and the reason why I can still talk to this chart 8 years later, this is the same chart that I'm talking to, and I'll tell you today that where are we? We're still in that early adopter phase, right? Why? Because there is so much misinformation out there about how NoSQL works, and people actually think that it's real, and there's blog posts, and there's all kinds of things that talk about using relational models in a NoSQL database. It breaks everything. It makes it worse than the relational database. When you figure out how it works, you have a better experience. And this is why what was most important to us at Amazon was getting those 25,000 developers, right, up to speed as quick as possible. So the first team that we worked with, we went down this process of, we're going to evangelize, we're going to do the same thing we always do. We're going to have workshops, we're going to do hackathons and this kind of stuff. And teams would listen to it. Oh, this is great. Wonderful. We're going to use this new technology. One of the first teams I worked with was the Amazon shopping cart team. They came back to me almost immediately, said, doesn't work, can't use it, we'll never be able to use it. And I was like, wow, that's nuts. Why is that? And if you think about the shopping cart, right, it's an interesting use case because people add items to the shopping cart, they delete items to the shopping cart. Right, they may keep a shopping cart in the system for God knows how many weeks or months or whatever, and then come in and make an order and delete 40 items out of the cart, And once you make the order, the items have their own life cycle, right? Inside of Amazon, they might get shipped out of different fulfillment centers, right? They're updated at different frequencies, right? When you check out, you'll see in the cart there's two different. Might deliver on this day or this day. If you click this button, it all delivers on the same day. You know what I mean? It's like there's all kinds of operations occurring on the data that's in the shopping cart. And this is a real clue because those little items inside the shopping cart, each one of those things, in DynamoDB, each one of these is about a kilobyte. DynamoDB is kind of merciless when it comes to cost. And the WCU is minimum, it was 1 kilobyte. And so if they added one item to the cart, it was a kilobyte. And they created an item for each shopping cart. And they started creating an array of items in that shopping cart. They create one item in the shopping cart, that's 1 kilobyte. They create two, now that's 2 kilobytes. They create three, that's 3 kilobytes. This is all WCUs, right? So all of a sudden, when you add the fourth item, man, you're paying for 4 items on that update because you're reading all the others when you're adding the one. Now you get someone who has 12 items in the cart and sits there and does that for 3 weeks, right? It becomes extremely expensive. So the team was like, it just can't work. There's no way to make it work. So the solution here was to avoid that effect of increasing the size of the item every time they added an item to the cart. And instead, in DynamoDB, we created a partition key, which was the shopping cart ID, and we created a sort key, which was the ASIN or SKU of the object, of the item in the cart. And now every update to the cart was adding an item into that partition. If you think of the partition, it's kind of like an index, right? A secondary index. The DynamoDB tables, the primary table, can have both a partition and sort key, so you can create an index-like structure, right? And that's what we did. We basically loaded these objects into partitions, and as we added and removed items, the WCU cost was constant, 1 kilobyte, never more. They cut their cost by 80% when they ran their workload simulations, right? So all of a sudden, it became an effective technology, right? So the key was that the team needed to learn how to use it, right? And so this was the exercise we actually started going through with various teams around the organization. Essentially, executing these design reviews to sit down with them just to get them started, right? Where's the trailhead? How do I get going down this path? My team specializes in doing this. This is what we do. We run the events we call MongoDB Day today. I used to call them DynamoDB Day when I was at AWS, but it's all about NoSQL, and it's all about learning how to model your data correctly for your workloads. I think I mentioned developer relations for strategic accounts, and within these accounts, I execute tailored engagements throughout the year where my customers tell me what is it they want to know about technology, and then we'll do the advocacy session like this. We'll do the half-day engagements where we'll talk about the technology, dive deep on aggregation framework, dive into the developer platform, whatnot. But the real meat for our customers is this exploration of data modeling, right? It's how does it work for you? We're going to sit down a couple weeks before the event. We're going to drive, my marketing team goes in there and drives attendance and signups and registrations from the various teams at the customer site. And I'll sit out there for a day, 2 days, 3 days with however many guys I need. I was just out in India, did a couple of events with over 1,000 developers. And the power of these events is tremendous because I'm not there to sell anything, right? I'm just there to show you how the technology works. You can make your own decisions. One of my favorite quotes in computer science is by Grace Hopper. Who knows who Grace Hopper is? I always have to do this, and I'm always surprised at how many people don't raise their hands. Grace Hopper, look up Grace Hopper. She had an amazing quote. She said, one accurate measurement is worth 1,000 expert opinions, okay? That is the cornerstone of my career. I cut my teeth in engineering and QA, and it's all about measuring things. We can argue back and forth all day. When I put the tape measure on the board, it's going to tell us how long it is. And that's exactly what this is all about, okay? So one of the things my team has, we have a great tool we call a schema bench, which allows customers to configure different schema options, even make different data sources. You can create the relational database version of your same, of your NoSQL schema, and you can run the workload. Run your access patterns. It gathers P95 latency, average mean, total throughput, and it'll just tell you. Look at the numbers. I can guarantee you'll never be able to configure a relational database that has the word join in that query and have it run faster or better or with higher throughput than I can run the exact same workload with the exact same result in NoSQL, and we'll measure it. I'll challenge you with that because it's just not possible. I just broke it down. It's right? Math doesn't lie, and time complexity is what it's about. If it's higher time complexity to run that query, it's just going to take longer. It's going to take more infrastructure, okay? So what it comes down to when we want to start working with NoSQL is about thinking in documents. And even wide column store, document database, whatever, you can call it's all documents because everything supports a JSON type, and nested data structures are just part of the business. So it's about thinking in documents, thinking in objects, whatever you want to call them, thinking in items. But the reality is what we want to do is we want to understand the access patterns, right? So what is the methodology that we follow? Same methodology for NoSQL, for any NoSQL database. It doesn't matter if I'm DynamoDB, MongoDB, whatnot. I've got a lot more API feature functions with something like a MongoDB. I've got a lot more indexing options and flexibility, but the core data models are the same. Okay, so the bottom line is I need to understand the workload. If the workload doesn't really have any velocity and doesn't have any size, then how much time do I really optimizing the data model, right? Probably not much. Maybe thing that runs a couple times a day, fine, just use large embedded documents, don't worry about how much those updates cost, it's not a big deal. But if it's, runs thousands of times a second, then I care. Okay, then I'm gonna wanna make sure that those patterns are highly optimized, for the particular use case that we're talking to. Once I understand the workload, it's about relationships, right? It's all about relationships. We need to understand the data model. We understand that logical entity relationship diagram. None of that goes away just because I'm using a NoSQL database. It's all extremely important to understand this because that's going to define how we set up or structure the documents that we're using and what kind of patterns we're going to apply, right? There's a whole bunch of design patterns. We've got some great content out there on MongoDB University that covers this stuff. And really, this is all my team does. It sits down and goes through the access patterns our customers have and decides, based on the entity relationship diagrams that we're looking at, we whiteboard all this stuff and we say, okay, here's what your documents might want to look like and here's the design patterns, that we're going to apply. So, it's what I guess you could call it a flexible methodology. It's about choosing simplicity or performance. This is you always have a choice, right? In any database, you can hand off to the ORM and let it run, and that's not going to give you the best performance. And then when you scale that system, the DBA is going to be coming in and going, what did you guys do? And he's going to, he'll unwind all this stuff and write real queries for you. But in NoSQL database, it's kind of important to understand that up front, right? What am I really modeling for here? Do I care about the efficiency of this model or not? If it's simple, I'm talking about generic patterns. I'm talking about embedded documents, really. I mean, I don't care how big they get. I don't care if I'm updating small pieces of large documents because it's not really a high velocity pattern that I'm supporting. We're talking pennies, not dollars. If I get performance, I'm talking about, if I don't do it right, I'm going to be hooking a fire hose up to my wallet. Right? And that can happen. That can happen with any database, and with NoSQL, it can happen really fast. So it's important to understand the nature of the workload that we're trying to model, right? What is the velocity? Because if it's a performance I'm looking for, then we're optimizing for common patterns. We need to be able to address the corner cases. This is the mantra of NoSQL data modeling, right? Optimize for the high frequency patterns, okay, while accommodating those corner case patterns. The ones that are those operational analytics, maybe that run once an hour, once a day, whatever, we don't really care about the efficiency of those queries. We just need to make sure we can support them. Again, the ones that run thousands of times a second, those are the ones we care about. So we're going to talk about a use case here. It's a pretty common use case for NoSQL databases these days. I see it a lot in the enterprise. They start with the idea of I want a single view of the customer, a single view of the data, and eventually I want to maybe create a new system of record for some of these back-end systems. So the idea here is we have maybe an insurance company built through acquisition, lots of back-end systems, miserable customer experience, customer logs in the online portal, it takes 45, 60 seconds to go hit all these back-end systems and get all the data and figure out who they are and everything. What they really want is they want to merge all that data from those legacy systems into an online portal that gives them a much better user experience, okay? It's going to be a read-only copy of the data. Essentially, there's no write operations occurring on this database, just updates coming in from the back-end systems that are being applied in batches throughout the day. But maybe, eventually, it'll be the future base of the customer portal, right? But the idea here is it's kind of read-only cache, offload those mainframes. It's a really good pattern, honestly. If you can offload a lot of the read velocity from those back-end mainframes, you actually breathe some life into those systems, right? Give them some more overhead to be able to handle additional writes. Okay, so works both ways to help the mainframe as well as help the customer here. So if we go through the process, right, what's the first thing we want to do? We want to understand the workload. So we're going to go through this process of identifying the access patterns. I hear all the time when I talk about, we went to access patterns and listing the access patterns, I hear developers say, but access patterns change and we don't really know what they are. And you know what, if you don't know what your access patterns are, you shouldn't be writing code. You should be writing user stories, okay? Because user stories define your access patterns. And if you don't have any of those, then why are we writing code? Okay, so code includes the query. The query is the access pattern, right? So as soon as I write a line of code that contains a query, I've defined an access pattern, we can start talking about the data model, okay? So let's do it, and let's do it up front. And so in this case, we've got really 4 patterns we care about. The first one is changes coming in to the Mongo Insurance portal from the back-end systems, right? This is the change stream from legacy databases. Comes in a pretty steady stream throughout the day. The rest of these are just read patterns, load user profile, load the overview of the account, load the detail of the artifact, kind of standard. Users got to work with their data, right? But when you start to look at the velocity of these queries, something becomes immediately apparent, right? We've got Streaming updates peaking at 2,000 transactions per second. These are critical writes. These are what's coming from those back-end systems, right? The rest of the stuff's no joke, right? I mean, users log in at a pretty good rate throughout the day, 12 reads a second on the various access patterns. But the one that's really hammering us is those streaming updates. Okay, and those streaming updates, something you kind of should already know about those is those updates are to what? Small rows. Right, small rows of data in the relational databases in which back all those services today. So small streaming updates coming in, that's a critical one as well. So if you think about the use case, again, it's a portal. We've got pretty standard, nav pane on the left, maybe some summary data about what messages we need are open, or claims, whatnot, detail information in the center, and as I nav through, click through the various objects, I'll open up details of those various artifacts, so on and so forth. So again, pretty straightforward user pattern. The next thing we want to understand is the data model, right? The logical entity diagram. And in this case, it's a very straightforward hierarchical data model. Customers have policies, have claims, invoices, documents, and messages. No many relationships here. I would probably say this is the most common style. It is the most common style of schema that I see. Maybe 30 to 40%, maybe a little over 50% of the time I see these types of hierarchical schemas. These are very easily represented in NoSQL databases. And we'll talk a little bit about how we'll do that when we get into applying the patterns, right? So we think about patterns, it's about, again, it's a trade-off, simplicity, performance. I'm going to get more into the design, I'm going to spend more time optimizing if I'm worried about performance. I'm going to spend less time optimizing if I'm worried about simplicity, right? So it's all about velocity. In this particular model, we're kind of seeing the type of velocity that means that performance is important. If I've got updates coming in at 2,000 transactions per second, I can't, I need to make sure those updates are happening efficiently, right? So it's not about, if I have one large document for all the user data, then eventually that's going to create a very large document with lots of arrays of embedded subdocuments. And as each one of those policies updates or a message comes in on a claim, I'm going to be reading the entire customer document to write that message right back into it. This is the most common mistake that you see in NoSQL databases. It's a mistake that the shopping cart service team made. Right, just going with that one document, hey, I'm just going to go maintain objects within this document. And honestly, some of the marketing information you get from MongoDB, it kind of perpetuates this idea, which is not really a great idea, that, hey, we support 16 megabyte documents. If you're using a 16 megabyte document in MongoDB, let's talk, because there's something wrong, and you're probably paying a lot of money to do something that is really bad, right? Even over a couple hundred kilobytes. Now, anything, I like to see small documents, right? Really small documents, like in the 4 to 10 kilobyte range. I mean, I don't like to see, documents much bigger than that, because typically access patterns, these high velocity patterns, right? If you think about it, 70% of access patterns hit a single row of data on a single table. How big do you think that row is? Not very, right? So, as a matter of fact, if it gets too damn big, then relational databases have triggers off-row storage, which causes all kinds of performance issues, right? So we don't want to go there. So the idea of keeping your rows or your document sizes pretty close to the row size is probably a pretty good one in most cases when you have high velocity updates coming in randomly across the schema, right? So that's kind of where we're going to focus here. We're going to use the extended reference pattern. This is what we call, one of the things I say, we keep a reference of one document from one document to another. The model I showed you earlier, we created target arrays of pointers, right? Those pointers were essentially references between the documents. We index those references. Essentially, we execute the join without having to incur the time complexity. So it allows us to efficiently query those documents that are related to each other to support those patterns much better. We'll denormalize if we need to increase the read. Honestly, I don't like denormalizing mutable data. I like if it's immutable data and it makes it easier to model, then yeah, why not? Why not? Storage is cheap, right? So if it makes it easier to do the model and it's immutable data, then absolutely do it. We do give you $lookup, which is a join operator, but don't do it if you don't need it. Right? I mean, no, it's there. It's like what I said. It's for those infrequent patterns, right? I need an hourly report across multiple collections. Great. $lookup's there for you. You can execute those types of queries. I need to run that report 1,000 times a second. Let's talk about something else, right? I mean, you're not going to need that. And you don't want to run that, right? So $lookup's really is a good tool, but like any tool, it has a purpose and a place. And if you use it inappropriately, it can really be expensive and less efficient than you would like it to be. Always remember that one read is faster than many. I hear a lot of people say, well, Rick, why don't I just put all those objects on multiple tables and index on order ID, right? And I can have shipments, invoices, and payments, and I'll just query everything at the same time, right? You may be able to achieve similar latency, but if you think about the overhead in a system, the overhead of establishing the cursor on a table is where it all comes in, handling the connection, right? 90% of the overhead a system incurs in processing a request is handling it. Marshalling the data and pushing it up there is nothing. Opening a cursor on a table is expensive. Returning a couple extra rows or a couple extra documents from that collection is negligible overhead. So if I can query one index instead of 5, I'm reducing the overhead on the system by like orders of magnitude. As a matter of fact, when I was at DynamoDB, I had an office hour session I did that demonstrated this, right? It did a single collection design or single table design versus a multi-table design. It was very clear, throughput, latency, apologies. So on and so forth. These things were all dramatically better when you push the data into a single collection or single table and you query a single index. So let's get into this real quick. If we look at that document structure, again, hierarchical structure, so what are we going to do? We're going to build a hierarchy, and in this case, what I'm going to do is demonstrate a technique I call key overloading. Use this a lot in DynamoDB, applies just as well to MongoDB. One of the biggest mistakes I see customers use in document databases like MongoDB is they don't use underbar ID. They'll stick a document in the database, they won't assign a value to underbar ID, they'll let the database automatically assign a value to it because that's the primary key, right? And it identifies the uniqueness of the document. But then you'll never have an access pattern that says get this document by ID. Right? You might have some other unique identifier that people store in the document, but they don't use it for underbar ID. The problem with this is that underbar ID is the default index on every collection in MongoDB, and you cannot turn it off. So every write is going to touch that index. That index is going to get loaded in cache every time that collection is opened, every time the database opens. And so essentially, if it's not being queried, then it's a dead index. It's a write-only index. It's a wasted resource on the server. So I always want to make sure whenever I talk to a customer and I see like an object ID and underbar ID, I say, do you have an access pattern that says get by underbar ID? And if they say no, I say, well, let's find another value, because you've got this write-only index, which is not great. So in this case, what we're going to do is use underbar ID in multiple ways. I'm going to make sure it has a meaningful value. For the customer document, it has the customer ID. This might be a UUID in prod or whatever. I'm going to use more human-readable data here. And then I'm going to prefix the keys of the rest of the hierarchy to create a path that I can query down, right, to get the subsets of documents that are interesting to me, right? If I want the whole history of a customer, I say starts with C1, brings back everything the customer has. I want just the policy data, select by C1 underbar P1, where it begins with C1 underbar P1. It brings back all of the data that is associated to the policy. If it's, so on and so forth. I want messages for a given policy, starts with C1, P1, M1, brings back the messages, subset or subdocument from this array of documents. What I've done, again, I've created a path on underbar ID using key prefixing so that I can select groups of these documents using a starts with condition on that key, right? I can pull the whole hierarchy easily with starts with C1 and get everything and so on and so forth down the path. This essentially allows me to support almost every access pattern I have with one index, the default index on this particular collection, right? So I'm as efficient as I possibly can be here with this data structure. The other thing I want to talk about a little bit is what we call the outlier pattern. This is where if I have like some data that grows, objects that grow over time and sometimes become too large, in this case we'll talk about messages, right? If I need to overflow data across multiple documents to prevent the write cost from becoming too high, if you think about what happens when messages come in, if I have a document that some customers might be really chatty and others not so much, but essentially what I'm doing in the messages document is I'm building an array of messages. And at some point that array is going to become large enough that it's going to become painful to update. Okay, it's going to become too expensive. And what I might want to do at that point is I might want to say, okay, let's break that document up. If my average customer talks 60 messages or less and my whales are talking more than that, then my whales are going to get multiple message buckets. And so we're going to create this pattern where those outliers essentially have more than one message document, and they end up with C1, P1, M1, C1, P1, M2. If I want to get the most current document, I can just say, starts with C1 P1 underbar M, limit 1, and it's going to give me the most current document, depending on which way the index is sorted. There's always a way to get the list of most current messages, but each message update is only going to cost me a minimum unit of cost. This is one of the most critical things to understand in document databases and NoSQL databases in general, right? Minimum unit of cost. We want to know how much it costs me to write into the database and what minimum size of document I need to have to be able to avoid that extra cost. Remember we talked about in the shopping cart scenario with DynamoDB, it's merciless, right? 1 kilobyte, 1 WCU, no compression on the data. MongoDB, not so much. We're a little better. We've got 4 kilobyte blocks in the storage engine, right? For Wired Tiger, we have compression. So my team these days calculates with mixed binary text data about 16 kilobytes. That's your minimum unit of cost, right? So if you got a document that's 16 kilobytes or less, then it's going to cost you the same to write that, whether it's 1 kilobyte or 16 kilobytes. There's still reasons why I might want to use really small documents, right? We can get into that depending on your access pattern. High velocity writes, low velocity reads, right? I don't really care. I'd rather just make sure that my writes are as efficient as possible. But the reality is in MongoDB, think of documents in that range. If I have full text data, I might see better. I have some customers getting 12:1, even better. Compression ratios depending on the nature of their data. So again, it all depends on your data, but understand that when you build your documents, at some point you can cross that line, it's going to cost you 2 IOPS. And at that point, if the access pattern needs it, great. That's fine. If the access pattern doesn't need it, then you're wasting space. You're wasting capacity, right? So always keep your eye on that and understand what's happening in your database. All right, so conclusions from today's talk. If you can walk away from anything from this discussion, understand that NoSQL does not mean non-relational data. There's no such thing. That's, again, the static in the air. We don't care about it. The ERD still matters, right? There's nothing you can do to get away from that. We still got to model the data. The relational database is done, okay? It is done. That you cannot get away from that time complexity. People talk about scale and things like this, right? And they used to say the relational database doesn't scale, Relational database scales just fine, okay? I learned in physics in high school, anything will fly, okay? Seriously, you give enough velocity, a brick will fly. Hey, that's how they fixed the space shuttle, right? The space shuttle wasn't supposed to fly, or it was, I guess, initially supposed to fly somehow, but they decided that the only way to make it fly was strap on a bigger freaking fuel tank, right? I mean, this is what you can do with the relational database. Yugabyte, CockroachDB, you name it, okay? They're just adding time complexity, distributed cross commits, Paxos, that just makes those equations longer, okay? If you can reduce your queries to O log n, you will reduce the amount of infrastructure you need. Database infrastructure is the #1 cost in the enterprise today for a reason, because the relational database is a waste. It's honestly, let's look at NoSQL. Let's do ourselves a favor. I could talk about that all day. NoSQL is a great fit for most OLTP workloads, right? It's a great fit for OLAP these days with those SQL read APIs, and that's what I've got for you today. Thank you so much.